Hello everyone, in the previous video we have studied about beats. And what is beats? Beats is the fundamental, this is the fundamental unit of classical information. So with the help of this beat, what can we encode? We can encode word. We have already seen we have encoded the color red, green, blue, blue and yellow, and also encoded the color of rainbow. We can also encode alphabet like A B C D, A B C D. Even we can encode character like greater than sign, equal than sign, less than sign, and we can also encode the pictures. Yes, this is new thing. We can also encode picture with the help of this bit. How we encode picture? There is a simple example of, let me take a very simple example of binary image. So suppose this is an image. It is divided into pixels. So let's suppose these are pixels. Pixel is a small unit. So suppose it is a rough idea I am giving you. Suppose this pixel is 1. So it will have a black color. Okay. Suppose this pixel has 0. So it has white color. It can be vice versa also. You can assume that 1 has a white color. Okay, so we generally take white color as 1 and 0 for the black color. I have written opposite, but you can assume like that. So now if we can encode pictures, then we can also encode video, because video is the picture per frame. Means, so video, what is video? Means 1 second. If there are 24 images running in 1 second, then it is 24 fps videos, right? So that is similar to that. In this video, we will be exploring how can we manipulate those those binary bit. Okay, we will be manipulating those bit. So how we are going to manipulate this bit? We will be manipulating this bit with the help of logic gate. Logic gates. We can use one gate, we can use more than one gate also, based on the purpose, based on what output we required. This logic gate can take one input, two input, or multiple input. Two input or multiple input. We will look one by one. One input, first see what is one input logic gate, then we will look for the two input, and then we will go further for the multiple input logic gate. So with the help of this logic gate, we manipulate the bit. And why we manipulate this bit? So that we can compute the functions, various functions we can compute with the help of manipulation the bit. Going first, we will look at single bit gate. Single bit gates. We will giving it one input and it will consist of one output. So let's look how this single bit gate looks. So see, this is one input. Suppose this is our gate. Now we have one output. This is input. This is output. Input. Let me write it completely. So we feed our bit information from here and we get the manipulated bit from the output section. Keep in mind that we always move from left to the right. Okay, so we will be solving our gate problem with from left to right, not right to left. Sometimes we can miss in quantum bit we can do so, in quantum gate we can do so, but not in the case of classical gate. We have to always move from left to right. Suppose now take the let me draw a table. Input and the output table. Mind my handwriting. I am using this tablet looking in the screen, so sometimes it can be little bulky. So suppose we have 2 bit 0 and 1. Suppose I am giving input 0 and suppose I am giving input 1. So what will be the output? So this output depends upon the gate. This gate. We can't change the input. We are feeding 0 and 1. We can change gate to get our required output. So if I talk about the identity gate, now here come one name, identity gate. So identity gate means identity 1. It will remain unchanged. So suppose if there is an identity gate, we generally represent by this. So suppose I am feeding an input of 0, I will get output of 0. Suppose I am feeding input of 1, I will get output of 1. Sometimes this identity gate is also represented by this long line. Basically means we are short circuiting, getting the same information. This is input, this is output. Now let's talk about NOT gate. NOT gate. So what is the function of NOT gate and how it looks? So let me draw a NOT gate. So this it is very similar with the identity gate except one dot, and we can further increase like this. So what is the function of NOT gate? Suppose this is input, this is output, and let me draw a truth table for you, and we give input as 0, then we will get output as 1. It is flipping those bits, means it if it is 0, then it is inversing it to 1, and if it is 1, then it is flipping it to 0. So if it is 0, then we are getting output as 1. If it is 1 as input, we are getting output as 0. So basically what is happening here, if we are giving A as input, we are getting A inverse at the output. Sometime this NOT gate is also called inverter inverter gate, since it is inverting the bit. And one more information, the identity gate is sometimes also written as buffer gate. This information is not very much required, but you can have a knowledge of general knowledge. Means if somewhere it is mentioned that inverter gate, use inverter gate, then you might get not confused with the identification of the gate. So now another gate which we will be looking at is the zero gate. It is also known as always zero gate. By the name itself, you can say that if suppose this is input and this is output, so whatever the input is there, we will always get output as 0. Same with the fourth gate, which is always one gate, means whatever the input, we will always get output as 1. So we have looked at um, which gate we have looked: buffer gate, means, or identity gate. Then we have looked for NOT gate. Let me write: identity gate or buffer gate. Don't get confused with the name. Then second we have NOT gate or inverter gate. Third we have always zero gate. Always zero gate. And fourth we have always one gate. So all these are the example of single bit gate. Single bit gate. where we are giving one input. Now let's move further and talk about 2-bit gate. 2-bit gate. By the name itself, you can assume that it will be having two input. So let me draw two input, and this is the gate, and we will have a one output. In classical, we will always be having a single output. So suppose this is first input and this is second input and this is output. In case of one input, we were having the combination of 0 and 1. Now since we have two input, we will be having combination. Suppose this is 0 1, we can fit 0 1 in this also, we can fit 0 1 in this also. Means, so how many combination will be there? Let's see. A, B, and this is output. Suppose we are feeding A as 0 and B as 0. Let's not discuss what will be output because gate is unknown. If we are feeding A as 0 and B as 1, another case will be A as 1 and B as 0, and if both A and B as 1. So these are the four possible combination of input for 2-bit gate. So now let us look at the possible gate, means what are the 2-bit gate. So the first gate which we are going to discuss is the AND gate. So how it looks? So we know that there will be two input and our gate diagram will be like this and a single output. So this is A, this is B, and we are writing it like A, B. So now let's draw the truth table of this AND gate. So we are having A and B and output. So we have how many? Four possible combination. Let's check. So what happened in this case? We will be having multiplication. Binary multiplication we will be having here. So what will be having? 0 into 0. We will get output as 0. If we multiply 0 into 1, we get 0. If 1 into 0, we get 0. And if 1 into 1, then we get output as 1. So suppose in a certain situation you want both the A and B should be 1, so that you want to pass, then only you want to pass that information as 1. In that case, you can use the AND gate. Now let's talk about the second gate, which is OR gate. So what is the logical operation of OR gate? A plus B. So we are adding. We are doing a binary addition in the case of OR gate. But it is not actually binary addition. Means if we add a binary number 1 plus 1, we will get 1 and 0, means 2-bit system we will get. But in this case, what we do, if we are adding 1 plus 1, then we will always get 1. So sometime in some book it is written as A plus B, but same it is written like A or B, this like. So let us look at the diagram of the OR gate. So how our OR gate, it is a two input, two gated, means two input gate. So its diagram look like this, and this as the output. So this is A, this is B, and in its logical operation will be A plus B. So let's go further and look at its truth table. So A, B, and here output. So possible combination 0 0 0 1 1 0 and 1 1. So 0 plus 0 you will get 0, 0 plus 1 you will get 1, 1 plus 0 you will get 1, and 1 plus 1 you get 1 from this example. Okay. So suppose in such any situation you want that if any of the input is true, you want to return output as true. In such case you can always use OR gate. Now let's talk about the third gate. So third gate is exclusive OR gate. It is represented by XOR gate also, means we write XOR. What is different from, means it is exclusive OR gate, means it will be having the output of 1, but means output of OR gate. But what is exclusive, what is different from the OR gate? So let's look and find out what is different here. So let me draw a diagram of XOR gate. So it look like this. So it is XOR gate where we have two input A and B, and we have output. So let's look at the truth table of XOR gate. So its operation is denoted like this. We know the possible combination 0 0 0 1 1 0 and 1 1. What happen in the XOR gate? If any one of these is 1, then only it will be 1. If both are same, then it will not be 1. So suppose this is 0 0, it will be 0. If this is 0 1, since one bit is 0 and another is 1, so it will be 1. In this case, for A input is 1, for B input is 0. So we will get 1, but in the fourth case, here what changes? Here A is 1 and B is 1, so we will get our output as 0. So one thing you have noticed that I have written like this: A and plus, then I have circled this, and then I have written B. So what is it doing? So this is, in mathematical, it is known as modulo of 2. So what it is doing, it is taking the addition and doing the modulo of 2. So what you mean by the modulo of 2, or basically modulus of 2? So if you want to represent 0, then its modulus of 2 will be 0, because 0 divided by 2 remainder is 0. If you want modulo of 1, then you will get 1, because 1 divided by 2, it is, you are getting 1 reminder. Here we are doing the absolute division, so no case of 0.5 like this. You are getting 1 reminder. Suppose you are for 2, the modulo of 2 will be 1. No, 1 not 0 0. Why? Because 2 divided by 2, you are not getting any reminder. Mind this, these all are reminder remaining. So 2 divided by 2, you will be getting 0. 4 divided by 2, you will get 0. 5 divided by 2, you will be getting 1. So this is how our XOR gate work. So now let us talk about our fourth gate, which is an A and D gate, or Nand Gate, or it is referred as not and gate. Means it is not and. So basically what it is doing, not and. So suppose this is our AND gate. Okay, and now we are putting one NOT gate here. So the combination of these is known as NAND gate. So what our NAND gate will do? So this is A and B, and this is output. So let me draw truth table. So this is A, this is B. Let me write one output here also for your, let us consider as C, and the final output. So how many combination of AB? 0 0, 0 1, 1 0, and 1 1. Now let's see what we are receiving at C. So if we talk about A and B, currently this is AND gate. So what if both are 0, then we will be 0, 0 into 1, 0, 1 into 0, 0, 1 into 1. Now here we are getting output as what we are getting output as C. So suppose it is 0, then it will be flipping it. Since this is not gate, so it will flip it. So what will be the final output? This will be 1. Since this is 0, this will be 1. Since this is 0, this will be 1. If this is 1, so this will be 0. So these are the possible output of the NAND gate. So for if we go about the logical operation, so this A input and B input will give, suppose these are input to our AND gate means NAND gate. So what we are receiving A, B, this is the algebraic expression of the AND gate, and then we are flipping this. So this is the algebraic expression of NAND gate. So we have already discussed around 4 two input gate. Now let's look at the fifth, which is NOR gate. I don't know whether it is correct sequence. If you are noting, correct it like this. If it is fourth, then write it is fourth. So our next gate is NOR gate. So what is NOR gate? Basically it means not or. Same as the previous case where it was not and, but here it is not or. One thing I have missed, I think so. So here I have given you a scattered diagram of the NAND gate where I have scattered the and not. But if you want to represent a NAND gate, you can represent it like this. So this is AND gate and one dot here. This is our NAND gate. Now talking about NOR gate. So NOR gate is the combination of OR gate and the NOT gate. Okay, this combo is known as NOR gate. So let's look at the truth table A, B. Let's consider this output as C. This is A, this is B, this is output. So A, B, C, and this is output. This is also output of OR gate. So what are the possible combination? 0, 0, 0, 1, 1, 0, 1, 1. So what is the output of this OR gate? OR gate. No. So 0, 0 it will be 0, 0, 1 it will be 1, 1, 0 it will be 1, 1, 1 it will be 1. So what will be the output of NOR gate? Means after we flip it. So 0 flipping it will become 1, 1, 0, 0 and 0. So from here you can understand that basically we are flipping the OR gate. Means we are only flipping the OR gate. So what will be its algebraic expression? We are giving input as A, input as B. Here our gate is there and we are getting output as A plus B. This is the expression of OR gate and we are flipping it to get NOR gate. So how we represent a NOR gate? So we represent NOR gate like this. So this is NOR and one dot here. So this is input and this is output. So I think video is getting long. In the next video, let me write the content for the next video. In the next video, we will try to solve, means we will try to write uh, some means some truth table for the combination of gate, for the combination of gate. Means today also we have written truth table of combination of gate. Here we are combining OR gate and NOT gate. Tomorrow we will try to combine OR gate, NOT gate and OR and AND gate also. Try to look at the combination of 2 to 3 gates. We will also, this is the first thing we will do, then we will be also looking at the physical circuit for the gate to perform gate operation. I will try to make animation if possible. Otherwise, we will go through the whiteboard also. But let me look if I can try and simulate or animate for the better understanding. So at last you can revise this video or look at the various textbook related with the gate. You can get bulk information about the gate and how the truth table works. So thanks for listening this boring lecture. I will see you in the next video.